planet Earth hundreds of millions of years from now. Imagine intergalactic explorers returning to their home world, seeking traces of ancient civilizations. They discover a planet transformed beyond recognition. The familiar continents we know today are gone. In their place is a single, colossal landmass, marked by immense mountain ranges and vast fields of frozen snow and glaciers. The thriving metropolis they hoped to find has vanished. Only a few shattered remnants remain, buried under tons of rock. Could this be a future vision of Earth? We explore the forces that could forge such a desolate world and investigate how the incredible power of colliding continents continuously shapes and reshapes our planet in an endless cycle of creation and destruction. Our world viewed from space reveals the distinctive pattern of land that forms the continents: North America, South America, Africa, Antarctica, Europe, Asia, and Australia. These massive landmasses, separated by oceans, help stabilize the environment with weather patterns hospitable enough for civilizations and cities to develop and thrive. Now picture a planet ravaged by storm-force winds, subjected to extreme temperatures, massive freezes, intense heat waves, and prolonged droughts. A world where cities are crushed and destroyed, where Africa overruns New York and London lies frozen at the North Pole. The geological future of New York is likely to be rather traumatic. North America and Europe are on a collision course. The world as we know it will become unrecognizable. This isn't a portrait of Earth after a global catastrophe. This is how nature will mold our planet many millions of years in the future. This astonishing transformation is just part of a natural cycle that has shaped Earth for the last 4 billion years and will continue until the sun finally destroys its surface. Today, our continents may appear solid, safe, and permanently fixed, but they are none of those things. These great landmasses are constantly in motion. Speed up the last few billion years, and you would see continents sailing across the globe. Powerful forces deep within the planet tear continents apart and then smash them together in an ever-changing cycle of death and rebirth. Oceans disappear, mountains crumble and rise again, landmasses form and reform. Colliding continents represent the mightiest force on Earth. When we examine Earth's history, we see it is defined by change. Change is part of nature, and this change continues today and will persist into the future. To understand how continents shape our world, we must travel back to Earth's very birth. 4.5 billion years ago, Earth formed from the debris left over after the sun's formation. Dust and debris collided and clumped together. Once these clumps grew to objects about half a mile in diameter, their gravity attracted more material. Slowly, these clumps grew into as many as 20 embryonic planets. As these new planets orbited the sun, they began to collide. One colossal collision with a planet called Theia, which also created the moon, obliterated Earth's surface. The energy from this impact made Earth incredibly hot, reaching about 11,000 degrees Fahrenheit, over 7 times hotter than the inside of a cremation furnace. Earth was a massive, molten ball of boiling lava. This was a primeval hell, bombarded by thousands of asteroids and comets. But deep within the planet, a process began that would lead to the first land. The heaviest elements, like iron and nickel, sank toward Earth's center to form a molten core. Lighter elements, including oxygen and silicon, rose toward the surface, erupting from volcanoes as molten rock. Slowly, Earth's surface cooled. Molten lava solidified into patches of crust, the seeds of the first continents. But even as the first land was born, it faced a battle for survival. Our planet was bombarded by a large number of asteroids very early in its history, causing tremendous dynamic change from giant impacts. Geology professor Sam Boring is an expert in early Earth and the genesis of continents. The question of when we had an early crust is interesting. He suspects we had an early crust from day one. The real question is how long that crust was preserved. When Earth was constantly bombarded by asteroids, the chance of preserving any small chunk of that crust was very low. The relentless bombardment destroyed the new planet's crust almost as soon as it formed. This recycling of the surface continued for many millions of years, but as the flux of asteroids began to wane and Earth matured a bit, the early crust likely lasted a little longer. Eventually, the barrage from asteroid impacts slowed. Earth's surface continued to cool, but the planet was missing one vital ingredient: oceans. The source of Earth's water has been a controversial topic. Most scientists now think many meteoritic bodies contained quite a lot of water. Water carried by meteors and asteroids may have formed the oceans that surrounded the first continents. Earth, 4.4 billion years ago. Our planet is now 150 million years old, and the first primitive landmasses have formed. They were not like the 7 instantly recognizable continents of today. They were just small rafts of rock floating on the mantle. But now, a type of rock appeared on Earth's surface that would form the nucleus of future continents, a rock buoyant enough not to sink into the bowels of the Earth: granite. In South Africa, in the Kaapvaal region southwest of Johannesburg, geologists examine ancient granite that has survived the ravages of time. These are the ancient remains of what some consider the first true continent. We're looking at the relics, the remnants of the first continental nuclei. This is one of the oldest, and certainly the best preserved, continental nucleus in the world. Geologist Alex Kister studies how granite formed the first continents. The rocks here are so important because they are remarkably well preserved, much better than anywhere else on Earth, allowing us to study the processes involved in forming these early crustal rocks. Kisters collects samples to date the age of the granite. They drill small rock cores and send them to a lab for dating. Dating rocks is complex because, over long periods, minerals can break down and reform into new rocks. Scientists look for an ingredient tough enough to withstand the test of time: zircon. This crystal forms inside molten rock as it solidifies. Even if the rock is destroyed, the durable zircons survive. Zircon is an incredibly interesting mineral. It incorporates uranium and excludes lead, setting up nature's own time capsule. To illustrate, imagine an hourglass as a newly formed zircon crystal. Sand in the top represents uranium. Sand in the bottom represents lead. Over millions of years, the uranium in the zircon decays into lead. Measuring the relative proportions of sand in the top and bottom reveals how much time has passed. Uranium's relentless decay into lead gives us a natural clock. Using this technique, geologists date this granite at 3.5 billion years old, making it some of the oldest rock on the planet. These rocks make up a major part of what is known as the Kaapvaal Craton. A craton is an ancient raft of rock, light enough to float on the mantle, around which a continent will grow. Ancient cratons have also been found in the heart of the Australian and North American continents. The Kaapvaal Craton in South Africa stretches for 463,000 square miles, almost twice the size of Texas. Without granite, the craton and modern continental crust wouldn't exist. Granite forms when minerals in the crust melt, react with water, cool, and crystallize. Because it is made of lighter minerals, granite is less dense than other rock in the mantle, so it floats on the surface and mixes with other rocks to form rafts of land. The Kaapvaal Craton isn't totally built from granite. The oldest rocks here are amazing pillow lavas exposed along the Kamadi River. 3.5 billion years ago, they formed under the sea as lava emerged from an underwater volcanic vent. Upon contact with water, the lava immediately gained a solid crust, which then cracked and oozed additional large blobs called pillows. These rocks are among the oldest we know, basically identical to pillow lavas seen on recent ocean floors or in settings like Hawaii. The Kamadi pillow lavas began life on the ocean floor, but were pushed up out of the sea to form part of a continent. But where did the granite come from? To create it, you need the right mix of minerals. A new theory suggests life itself may have provided the missing ingredients. It may sound outlandish, but evidence indicates that living organisms using photosynthesis appeared around the same time continents began to grow, 3.8 billion years ago. Scientists suggest early microbes helped speed up the breakdown of rock emerging at Earth's crust. Over hundreds of thousands of years, this rock broke down into new minerals, which sank back into the mantle. Deep below the surface, they heated up and formed granitic magma. The magma rose into the proto-continent, froze, and formed huge solid rafts of granite. Now stabilized, the Craton began to grow, forming new baby continents. But Cratons aren't the only factors at work. More powerful forces were building deep within the planet, forces with the power to rip landmasses apart and smash them together, changing the face of the planet forever. 4 billion years ago, Earth formed. For many years, it was bombarded by asteroids and meteors. Slowly, the molten planet cooled, and small landmasses formed around cratons of granite rock. Massive forces from deep within the planet ripped apart and smashed these small proto-continents together as they grew into the large landmasses we see today. Earth's surface, the crust, is made up of a giant jigsaw of interlocking pieces called tectonic plates. The separate plates sit on the mantle, a layer between the crust and Earth's core. Although the mantle is made of rock, the heat and pressure deep down make it flexible enough to allow the plates above to move up to several inches a year. Evidence for the theory of continental drift was first proposed in 1912 by German scientist Alfred Wegener. He noticed identical fossils discovered oceans apart. Paleontologist Professor Mark McMenamin of Mount Holyoke College in Massachusetts is an expert in fossil records. Wegener noted that a freshwater organism cannot cross a salty sea. So if you find fossils of a freshwater organism or a land creature on two continents, now greatly separated by distance, they must once have been closer together. By identifying similar fossils on different continents, scientists can map which continents were joined in the past. Fossil distributions tell us where fossils occur and how the continents must have been juxtaposed. Fossils that are identical but occur in very different parts of the world imply that continents have drifted. When Wegener first proposed his theory of continental drift, he was laughed at. The idea that continents could actually move was considered preposterous. The problem was he didn't know how the continents moved. The missing mechanism wasn't discovered until the 1960s. Plate tectonics is powered by heat. It is largely driven by the fact that Earth's interior is much hotter than its surface. The temperature at the center of the core is 10,000 degrees Fahrenheit, as hot as the outer parts of the sun. Much of this heat is left over from collisions and massive bombardment during Earth's early days. The rest comes from the radioactive decay of heavy elements in the core. Heat escaping from the core creates convection currents in the next layer, the mantle. The process is like a lava lamp, where heat from the bulb at the bottom creates convection currents in the oil, pushing the synthetic lava upward. The heat melts part of the mantle and sends plumes of magma molten rock rising to the surface. It rises between cracks in the plates, creating new rock that pushes the plates apart. Plate tectonics is virtually inescapable on this planet. It's an exceedingly efficient way to cool Earth's interior. This formation of new rock splits apart and separates the plates and the continents sitting on them. Today, most of this new rock forms under the sea, creating vast interconnected volcanic mountain ranges extending through all the major oceans. One range can clearly be seen at the bottom of the Atlantic Ocean along the Mid-Atlantic Ridge. It stretches more than 12,000 miles from the subantarctic to the Arctic. It comes to the surface in a few places. Iceland was created from volcanic lava bubbling up at the junction between the North American and Eurasian plates. It's one of the few places on Earth where you can actually see continents being pushed apart. We are watching geological structures you cannot really see anywhere else. It's like a big textbook of geology. This is where Earth's crust is being made. Paul Einarsson, professor of geophysics at the University of Iceland, monitors the mid-ocean ridge where continental plates are splitting apart. The ridge in Iceland is almost 3 miles wide. On one side is the North American plate, on the other, the Eurasian plate. The rift here grows as new rock forms at its center, pushing North America and Europe away from each other. The Atlantic Ocean widens, and the two continents drift apart. Eventually, the Atlantic could become as big as the Pacific. To measure how fast they're splitting, Einarsson takes global positioning system readings at specific points along the plate margin. They put the antenna right on top of the point and calculate the exact position of this point relative to Earth's center. Although the ridge appears calm and no magma is rising to the surface, Einarsson's measurements show the two continents are drifting apart by around an inch a year. So by the end of the century, Europe and America will be almost 8 feet further apart. The movement in Iceland is typical of the processes shaping continents since their birth 4.4 billion years ago. It's part of the great cycle of Earth's continents. The new crust created at the mid-ocean ridge moves away, cools, and eventually sinks back into Earth. When the first proto-continents formed, there were several interconnecting tectonic plates, constantly bumping and grinding against each other, pushing new land over the planet. Today, Earth has over a dozen plates, some colliding, some moving apart. They are powerful enough to move a continent the size of North America over 3,000 miles in 200 million years. That's 15 miles every million years. Earth 3.4 billion years ago. Plate tectonics pushes proto-continents together. They combine to form ever larger tracts of land. Scientists suggest Cratons combined with other Cratons to form a supercontinent, a huge continuous stretch of land called Vaalbara. Scientists are unsure of its exact shape or size, as only a few pieces, like the Craton in South Africa, still remain. But Vaalbara's days were numbered. A rising plume of heat grew beneath it, about to rip the world's first supercontinent into pieces. 2.7 billion years ago, Vaalbara, the world's first supercontinent, still dominated the planet. But plate tectonics, powered by heat from Earth's core, was about to split it apart. Rock is a good insulator. When a continent gets very large, the rock traps heat beneath it. As it gets hotter, a plume of superheated magma builds up beneath the giant continental mass. The temperature continues to rise, and pressure in the mantle increases. Eventually, the crust can no longer contain the pressure, and hot lava breaks through, ripping the land apart. You can see this process happening today in Africa. Heat from Earth's core is ripping the continent apart. A giant rift valley runs from the Red Sea down to Mozambique. Giant cracks are opening in the land. Volcanoes like Kilimanjaro mark spots where molten rock has risen to the surface in the past. In 10 million years, the eastern half of the continent will have split away. The molten lava trapped beneath the giant supercontinent Vaalbara eventually smashed through the surface rock. The continent ruptured into several smaller pieces. These bits of land sailed across Earth, but nobody knows what happened to them or what the planet looked like at this time. Earth was entering the Dark Ages. It was over 2.5 billion years since it formed. Over a billion years would pass before another supercontinent formed. Earth was entering a deadly cycle of destruction and rebirth. The theory of continental drift suggests we go through cyclic phases of continental dispersion and then continental collision. Continents seem to move apart from one another and then collide over 100 million year or longer time scale. When a large continent splits apart, the separate pieces travel away from each other, pushed by the creation of new land at the ridge between plates. Because Earth has a constant surface area, the same amount of land created must be absorbed into Earth. This process happens at subduction zones at plate junctions. At a subduction zone, crust dives down into the mantle to be melted and form new rock. When the plate subducts into Earth, it brings two pieces of land together. When they collide, a new supercontinent starts to form. It is now 1.1 billion years ago on our timeline, and the next known supercontinent has formed. Its name is Rodinia, and it holds almost all the continental rock on Earth's surface. Still, no one knows exactly what it looked like, but at its heart is an area that will eventually become North America. 350 million years later, the cycle of annihilation and creation starts again as the buildup of heat beneath Earth's surface tears Rodinia apart. When Rodinia splits, it forms several smaller continents that, for millions of years, drift apart and then drift back together to form Gondwana, a supercontinent in the southern hemisphere. Eventually, after several hundred million years, Gondwana slowly splits apart. Plate tectonics push the land back together to create the world's last supercontinent, a huge landmass known as Pangaea. All the continents we know today were joined together. Geologists can plot the continents' relative positions because 350 million years ago, numerous species lived on Earth, each in distinct regions. This specimen is the first trilobite ever described from what is now the United States. It is exactly the same type of trilobite that occurs on the other side of the Atlantic Ocean in North Africa. So we know the trilobites in the Old and New Worlds must have been close together because they're so closely related. The fossil records show North America and Europe rested next to one another. The land where New York now sits was next to Morocco in North Africa. The Atlantic Ocean did not exist. The east coast of South America nestled against the western coast of Africa, while Australia, India, and Antarctica were joined to the southeast of Africa. If we look at a picture of the world 250 million years ago, we see a world in which a four-footed creature could walk from one end of this landmass to the other. Pangaea was one giant continuous landmass. It not only made the world look very different, but also had a dramatic effect on climate. Because much of the land was located far from the sea, the climate of the interior changed radically from season to season. It got very hot in the summer and extremely cold in the winter. You didn't have the moderating influence of the ocean we have today, so it was a very different world, harsher and less hospitable, at least to life on land. It's thought the climate change caused by Pangaea's formation may have played a role in one of the largest mass extinctions on Earth. This event, known as the Permian-Triassic mass extinction, wiped out about 90% of all life. It's been called the mother of all mass extinctions. The formation of Pangaea, with its climate-worsening effects, is considered a contributing factor, though not the sole cause. 250 million years ago, the supercontinent Pangaea began breaking up. The continents we know today began to take shape over the next tens of millions of years. South America drifted away from Africa, North America away from Europe, Australia split off from Antarctica and headed north to warmer climates. The positions of our continents were becoming familiar, though their distinguishable features were not. The world's vast mountain ranges, like the Alps and Himalayas, and its great valleys, like the Grand Canyon, were yet to form. They would emerge from one of nature's biggest battles, the battle between colliding continents. Earth, 100 million years ago. The continental map of the modern world was gradually becoming recognizable, but a battle still raged between continents that would change Earth's face forever and create some of the most extraordinary geological features. As continents moved slowly across Earth, crust and rock were dragged back down into the planet at subduction zones between tectonic plates. But when continents collided at plate junctions, sometimes there was a battle for supremacy. If neither plate would submit and drop down to be consumed by the mantle, both continents slowly smashed and ground into each other. These pinch points of continental collision built mountains. The Alps are the largest mountain range in Europe. Higher than the Rockies, they stretch from France in the west through Italy, Switzerland, and Austria to Slovenia in the east. Their formation resulted directly from a continental collision between Africa and Europe. The story of the Alps began when the African plate broke away from the South American plate and started moving toward Europe. Without plate movement, there wouldn't be any mountains on this planet. Professor Gerard Stampfli of the University of Lausanne in Switzerland studies the processes that built the Alps. The African and Eurasian plates started moving toward each other, trapping a third, smaller Iberian plate between them. The three plates collided. The Eurasian plate was pushed downward into the mantle, chopping off the Iberian plate. The Tethys Sea began to close. As the Eurasian plate ground underneath the African plate, it pushed the Tethys seafloor and part of the Iberian plate 600 miles north and many thousands of feet into the air. Rocks that started life on the ocean floor ended up at the top of the Alps. It's quite fascinating to imagine that if you are on top of the Matterhorn, you're actually standing on top of Africa. For geologists, Africa stops in the Alps. Over the next 100 million years, continents continued to smash together. New mountain ranges started forming around the globe. The largest, the Himalayas, formed as the Indian plate charged northward toward the Eurasian plate. It moved at 2 inches per year, lining up a head-on collision. The movement of the Indian plate led to a clash between two giant continents and created some of the highest structures ever to exist on Earth. The incredible power of continental drift not only built mountains, but also sculpted one of the world's most recognizable landmarks. The Grand Canyon in Arizona. The Grand Canyon is a great scar on Earth's surface. Geologist Ron Blakey has studied the canyon for over 30 years. It's a wonderful place to come face to face with planet Earth. The Grand Canyon is 277 miles long and up to 18 miles wide. At its deepest, it stretches down for over a mile. The gorge exposes the interior of the North American continent. It's like looking through the pages of a book. Each layer tells a story about the past. One of the neat things about the Grand Canyon is that as we go up its walls, it's like going through a time machine. Layer upon layer of rock reveals the geological history of North America from present day to 2 billion years ago. The deeper you go, the older the rocks. By studying the layers, Blakey pieces together the canyon's history. He finds some of the most interesting evidence at the very top, fossils of ocean creatures. This bed is the jackpot here. We have an extraordinary example of a Permian seafloor. The most important thing it tells us about the Grand Canyon is that this area had to be near sea level when these rocks formed. Now it's 7,000 feet above sea level on the rim, so something had to happen. Either the sea had to fall 7,000 feet, and we're pretty sure that didn't happen, or this landscape had to be uplifted 7,000 feet. We're pretty sure that happened. 250 million years ago, the canyon began to form as a result of a collision between the Pacific and North American plates. They collided with such force that the North American plate thrust more than 2 miles upward. What was once seabed rose over 15 million years to form a vast plateau far above sea level. It stayed that way for millions of years until transformed by water erosion. 6 million years ago, several hundred miles south of the canyon, plate movements opened the Gulf of California to the sea. For the first time, small streams in the Rocky Mountains could empty into the ocean. So if you're starting a stream at 14,000 feet in the Rockies and carving down to sea level, and the Grand Canyon just happens to be in the way, the Grand Canyon is going to get cut out. These streams merged to form what is now the Colorado River. It cut down through the land heading to the Gulf of California. It took a river to carve the canyon. The water carved down through the rocks layer by layer, removing material and leaving the great void we see. The Grand Canyon is a testament to the awesome power of continents in shaping our world. Back on our journey tracing the birth and death of continents, it is now 20 million years ago. 2,500 miles south of the Grand Canyon, another plate collision is about to take place. The map of the modern world is almost complete. At this time, water flowed freely between the Pacific and Atlantic Oceans, still separating North and South America. Over many millions of years, the Pacific plate began sliding under the Caribbean plate. The pressure caused underwater volcanoes to erupt. Some exploded with such ferocity, they created a range of small islands between North and South America. Over the next 17 million years, ocean currents deposited sediment in gaps between these new islands. Gradually, sediment built up and compressed to form land bridges. 3 million years ago, the Isthmus of Panama, a narrow strip of land, finally joined North and South America. It separated the Pacific and Atlantic Oceans. The flow of water between the two stopped, and ocean currents had to take new routes. This caused yet another change in our planet's climate. It altered the movement of warm seas around the globe, disrupting weather patterns and possibly pushing the planet into an ice age. Many species were wiped out. The continents as we know them today were formed, creating a hospitable environment for human civilization to evolve and thrive. But how long will it last? The forces that power plate tectonics are still active and will tear our continents apart once again. They will build a new world, one that may trigger another mass extinction and push humanity to the brink. A view from space reveals Earth's continents as we know them today. There are 7 in total, though some are separated by political rather than geographical divides. Africa-Eurasia is a supercontinent comprising Africa, Europe, and Asia, stretching from the Siberian Plateau in Russia to the Cape of Good Hope in South Africa. a spectacular route across 3 continents incorporating dramatic climate change, vivid scenery, and diverse cultures. However, Africa-Eurasia isn't the only supercontinent. Because Panama links North and South America, they too can be thought of as one vast landmass. And if the Bering Strait between Russia and Alaska were to freeze over, it would be possible to walk from Cape Horn in South America to the Cape of Good Hope in South Africa, a journey of around 25,000 miles. But this won't always be possible, for powerful forces deep below continue to send continents hurtling across the globe, a process that started at their birth 4.4 billion years ago and will continue long into the future. What we observe now is only a snapshot of Earth's global cycle, ongoing for the last 4.5 billion years and likely to continue even if we're not around. The global continental cycle has another impact. It causes many natural disasters. Plate movement creates stress points leading to volcanic eruptions. As continents split apart, instability at plate junctions causes earthquakes that rip apart communities. One on October 8, 2005, in Pakistan-administered Kashmir killed nearly 75,000 people and left up to 3 million homeless. And when plates subduct into Earth, their death throes produce devastating waves. The 2004 Indonesian tsunami is one demonstration of the terrifying power unleashed when plates move. Such natural disasters are part of the continental cycle and won't stop. Plates moving is something we have to live with. There's nothing we can do about it. It is going to happen. There will be big earthquakes in California, a lot of damage and loss of life. In recent years, it seems natural disasters powered by continental movement have been on the rise. But what we're witnessing is an increase in awareness rather than an increase in the number or severity of disasters. We have a very raised public consciousness with instant communication abilities. Much more publicity is given to volcanic eruptions and earthquakes. We are observers for only a very short period of Earth's life. If we could monitor earthquakes and volcanic activity caused by plate movements over millions of years, we'd see a very different picture. Over 10 years, you might have 10 major earthquakes. The next 10 years, you might have none, but that's not significant. It's just related to the short observation period. Over hundreds, thousands, and millions of years, it all averages out. It's impossible to predict exactly when the next disaster will occur, but possible to predict where, at plate boundaries. Map the location of earthquakes and volcanoes, and they line up with cracks between plates. Plot where these plates will move over the next tens of millions of years, and the future looks bleak for many world cities. So, what will our world look like in the future? 50 million years from now, the Atlantic Ocean will widen, pushing New York further from North Africa. Meanwhile, in the southern hemisphere, Australia will be on a collision course with Southeast Asia. In Europe, Africa will head north, closing the Mediterranean Sea. A new mountain range will form where Italy and Greece once stood, known as the Mediterranean Mountains. They will be as big as the Himalayas, extending from Spain across southern Europe through the Middle East and into Asia. 100 million years in the future, the power of continental movements will render Earth's surface unrecognizable. The Atlantic Ocean will continue to widen, but a subduction zone will form along its western shoreline. The first sign can be seen today in the Caribbean, the Puerto Rico Trench. This trench will grow north and south along the east coasts of North and South America. This vast subduction zone will consume the Atlantic Ocean, dragging Europe and Africa back toward the Americas. 250 million years in the future, intergalactic explorers returning to their home planet will find a world very different from records. There will no longer be 7 continents, but one gigantic landmass containing most of Earth's land. They might find it a barren, frozen world. Explorers search for remains of our cities. But when Europe and America collide, any cities along coastlines will be gradually destroyed. The geological future of New York is going to be rather traumatic. In the long term, New York will be at the site of a continental collision. North America and Europe will collide and produce a distinctive suite of rocks, eventually crumpled between the 2 continents. New York and its neighbors will be crushed and buried beneath the surface, leaving only a few remains. Future geologists will find remains of New York City trapped in rocks, buildings, plastic bottles, old nuts and bolts. All these will be incorporated into the fossil record and recognizable to a future geologist who knows what to look for. Because of similarities to past supercontinents, this future landmass is called Pangaea Ultima, the final Pangaea. Nearly all landmasses will be joined. Pangaea Ultima will probably experience climate extremes, freezing winters and scorching summers. This deadly weather could have devastating effects on all life. The implications for the human race are interesting to speculate about. Certainly, the disposition of continents over time will affect Earth's climate, influencing which organisms survive, which go extinct, and could be a factor in future mass extinctions. The world we know is inching slowly toward its own destruction. The processes shaping Earth's surface will never change. We will have earthquakes, volcanoes, tsunamis, and hurricanes regardless of whether humans inhabit the planet. The planet will always be here. Plate tectonics will operate for the foreseeable few hundred million years. The question is whether humans will be here to witness it, but even Pangaea Ultima might not be the end. The forces that created it may eventually rip it apart and start the cycle of death and rebirth again. But by then, the impact of colliding continents could have been too much for our species. With cities destroyed and climate severe, we may have already left our planet in search of a safer home. If you found this journey through Earth's past and future fascinating, make sure to subscribe for more explorations into our planet's incredible story. Give this video a like if you enjoyed it, and share it with someone who would find it intriguing. Thanks for watching.